Okay, so we started discussing conditional expectation, and there was one more property. One more property. So I'm reminding you what conditional expectation is. The expectation of a random variable with respect to a sub-sigma algebra is the unique, or almost surely unique, random variable that is G measurable and satisfies that when I take this random variable, multiply it by an indicator of an event in G, I get that the expectation of this thing is equal to the same thing if I put an X here. Okay. Discussed how to think about it, and you should notice that this is what is getting replaced. So as long as you're looking at indicators of events in G, you can replace X with this new random variable. It's a coarse graining of X in a certain sense. So it has less information because it's looking at a sub-sigma algebra, it's G measurable. But you average X on the pieces and you get something. Okay. So here's a property or a proposition, and this is called the tower property. Tower conditional expectation. So we have probability space. Then we have two sub-sigma algebras. One is contained in the other. So we have G and we have H, and they're sub-sigma algebras. And then we want to say, well, we can do the conditional expectation of X with respect to G, and that's a new random variable. Okay, so yeah, have this way. X is in one of a probability space. So we have a probability, we have an integral on the variable, we can take its conditional expectation. And then we have a new random variable, so we can take this conditional expectation with respect to a new sub-sigma algebra. Right? We're allowed to do that because we said that this is integrable. The integral of its absolute value is bounded by the.
We're not going to prove the existence
of a conditional expectation? No. I said it's Radon Nikodim. It's basically Radon Nikodim, and it's orthogonal projection if you are willing to work only in L2. So I'm not going to give the proof. If you want, it's in my book. It's using Radon Nikodim derivative is a few lines. Okay. If you want like the full Radon Nikodim theorem, then you should go to Duet or some classical measure theory
with the Ilan.
Okay. So we can ask for this conditional expectation, and it turns out that this is equal. And of course, when I write equality between two random variables, what I mean is equal up to measure 0. So this is almost surely equal to the same thing if I went the other way around. If I first sorry, what am I saying?
X to H.
Yeah, if I first did this and then did this, but now I want you to be very careful and notice that this thing is G measurable because H is a sub-sigma algebra of G, right? And we said that the conditional expectation of something that's G measurable is just thing itself. Okay, so this is why it's called the tower property. Tower property means that the tower collapses. You have a tower of sigma algebras. The smallest sigma algebra always wins, no matter which direction you.
Like you have like a sub claim here that gives to commit. Makes sense.
Well, I'm going to prove. So this equality is immediate. Okay, so yes, I'm going to prove everything. Okay. So this equality, this just follows because H is a subsigma algebra of G, and so this is H measurable, implying that it's also G measurable. Okay, so that's the whole proof of this equality. We showed yesterday that if you take something that's G measurable and take its conditional expectation, you get back the original thing, right? It's constant with respect to the information that you have. So it's just like the expectation of a constant, right? In fact, we showed something more general, right? Even if I multiply this by a different random variable, then this would come out and the other one would stay inside. It acts like constants. So what we need to show is the equality between these two cells. Okay, this is the actual tower. Okay, so what is the proof? So again, we're using the uniqueness of conditional expectation, right? We're using the uniqueness property, which is an easy property. I didn't prove it, but I claimed in the definition that there is an almost surely unique random variable that satisfies these conditions, right? And actually, uniqueness is very easy to show. And if you think about it for a second, you take a specific event A, you have two versions of this guy. They put here a Y and a Z that satisfy this, and they're G measurable, then you can choose a certain event A so that you find out that actually Y is equal to Z with probability 1.
I think the points for which they're different.
Enough points for which they're different has a measure 0. Okay, so you have to, well, you have to use something. You have to use, like, for example, you need to use that the expectation of a non-negative random variable is 0 if and only if the random variable is almost surely 0. Use that for some indicator here or for some random variable that you look at. And you should be a bit, you should think about it a bit, but uniqueness basically just follows. As soon as you know that things satisfied, you get uniqueness for free. The existence is the one that uses Ladon-Nikodym derivatives. So I want to prove this equality. So what do I need to show if I know the uniqueness? Just like yesterday, I want to show that this is a version of the conditional expectation of this random variable with respect to H. Okay, to make a notation or to make the proof kind of transparent, let's call this guy Y. Okay, let's call this guy Y. I just define Y to be the conditional expectation X with respect to G, using, of course, the fact that H is the smaller sigma algebra, right? It collapses to the smaller one. So I use this fact, and so I want to prove that the conditional expectation of Y with respect to X, with respect to H, is this random variable. Okay, so let's call this one Z. Now, Z is H measurable, right? So all we need to show is that it satisfies the second condition, so that if I multiply Z with an indicator, take expectation, it should equal to multiplying Y with an indicator and taking expectation. And the indicators have to be of all events in H, because I'm conditioning on H, right? So we take some event in H, right? And then we look at the expectation of Z times the indicator of this event. And this we have to find out that it's equal to the expectation of Y times the indicator. Okay, that's all we need to show. Because Z by definition is H measurable. Okay, so what is this? Well, let's write it down. This is the expectation of X H times indicator A. Now A is an H. So indicator A is H measurable. I can pull it in. Right? This is what we showed yesterday. So I can pull it in. I get, it looks like black magic, but you just have to get used to working with these things. Okay?
Just by definition, isn't it the integral of x? Okay, it would be the next step.
Yeah. I split it into two steps. Yeah, but you're right. Okay? So now this is the expectation of conditional expectation, and we prove that this is equal to just the expectation of the random variable inside. So this is this. Okay, but this is the expectation of random variable times something in H, times indicator of something in H. This is equal, by definition of a conditional expectation, to the same thing with the conditional expectation here. That's not what I wanted. I want Y. Okay, so yeah. Right, so I want to get a Y here, right? And this I'm going to use that A is G measure. A is in G as well, right? So this is equal to the expectation of the conditional expectation of X with respect to G, because that's what I want to get in here, times the indicator of A, right?
This is because A is also in G.
Because A is also in G, right? And then when I have this, then I realize that this is just what I was saying. This is Y, and so this equality for every event in H, this is not true for general events in G, but it is true for every event in H. So this equality tells you that Z is a version of the conditional expectation of Y with respect to H. Okay? It's not that Z is Y, but Z is the conditional expectation of Y.
One question that I didn't follow, like you have the first line, right? And then you have the second line. I understand the left equality. Sorry, the right hand side equality. But why is the left hand side?
This one?
Yes. Because the definition is
Because A is H measurable.
Right.
So this indicator is H measurable. And we said that conditional expectation, if you take a random variable which is H measurable, it acts like a constant. You can pull it in and out. This is what we proved yesterday. This was a theorem that we proved yesterday.
You need to choose which property you want to use, the property or the definition of the
because this is simply the definition, right?
This is just Z, so this is nothing.
on the diagonal
Okay.
to the right.
This is a theorem from yesterday.
Yeah, but we actually don't need
We
it.
don't need this, right? Because the right hand side is just the definition of the
Conditional expectation. Taking the expectation of.
You need to go from here to here directly. You're right.
Okay.
You can go directly. Yeah, I agree.
So this is what threw me off.
Okay, yeah, sorry. It's not wrong, it's just maybe.
Wait, so in general, the conditional expectation of a measurable function on H, simply the expectation of the random variable,
No,
like the equality you wrote from the left hand side to the right hand side. This one, yes.
Yeah.
Why is this
this
true?
with this,
Yes. Why is this true?
so, this is just expectation of conditional expectation is the expectation of the original random variable. Is that what you said? Okay,
Yes.
so
Yes.
that we also said yesterday.
Yes.
Well, I mean, I gave it as an exercise, but you can see it because take A equals omega. Okay? Okay, so this was the Tower property, and this is what I wanted to, and this concludes my short summary of conditional expectation. You can read more in any probability or measure theory book. And for conditional expectation, you want to talk about it. Okay, and I want to move to martingales. Martingales are super central, and I would teach them even if we weren't doing harmonic functions. But if we do, when we do harmonic functions, you'll see that I really want martingales, because basically martingales and harmonic I mean, it's Yale's not here, right? So martingales are the right way to look at harmonic functions. The right way to approach harmonic functions, because harmonic functions is just, in a sense, a different way of looking at. Well, it's a special case of martingales. Harmonic functions. Okay, so martingales. Now, what is a martingale? A martingale is something to do with horses. I think it's the bridle of a horse or something, it has to do with horse racing. Okay, now because these methods, so the name comes from the fact that people were gambling in Victorian England or something. There was I think the whole high society in Victorian England was addicted to gambling or something. They would have horse racing and lots of stuff, and then they were developing, of course, methods to win. Right, some people were even thinking about it because they had some lords in England had time on their hands. They frowned upon to have a real job. So this is why today's professors are the new nobility. So what they would so they were thinking of methods, and one method they did was the following. So suppose we're playing a very simple game. We'll talk about this game in the future also. So maybe it has a 50% chance of winning or losing. And what I can do is I can bet $1, and then with probability half, I get $2 back, or lose my dollar with probability half. If I lose, I bet $2, right? And then with probability half, I'm going to get 4 back, right? And so on and so forth. Every time I lose, I double my bet. You can check.
Positive.
I will eventually, it's a geometric on the variable, I will eventually win, right? And when I win, I will be up by $1, I guess. Exactly, because of the way 2 to the n sums, right? Now, some people had, this is called the martingale strategy, and from this came the name of these things. Okay, if you think about this game of plus minus a half each time, instead of thinking about doubling my bet, but just think of winning $1 or losing $1 with probability 1/2, right? If you think about what it does is that if you tell me how much money you have at current, including negative sums. So if you tell me where you are on the integers in terms of winnings, okay, doesn't matter where you started, right? On average, after the next game, you will still on average have the same exact amount. So conditioned on exactly the amount that you have in your hand, right? Conditioned on the past, your expected position in terms of how much money you have is exactly what you have now. So this is a martingale. That's basically the idea behind the martingale. And it's, when I double my bets, you can think of the log of that. So that's going to be, right? Log 2 of that is going to be the log. So this is a martingale. And so let's define it. Okay, so definition. So I'm going to call it a stochastic process. I'm going to say this out loud. When I say stochastic process, I just mean a sequence of random variables. That's all I mean. That's all I mean. Usually they use continuous time, so it's something else. But stochastic process is just a sequence of random variables because we're going to use discrete time. So usually we'll index them from 0.
Sometimes I see stochastic process when there is another assumption where you're not dependent on the time or something like that.
That's something else. That's a time independent. I'm not talking about Markov chain. Just most general definition of a stochastic process is just a family of random variables indexed by some well-ordered set. Well-ordered sets, it's R or parts of R or the integers or parts of the integers. So but since we always do discrete time, so when I say stochastic, just a shorthand for saying a sequence of random variables. Okay, so
does it have to be independent or?
No.
Sure.
They're not going to be independent in general. So it's just a way of saying it. I'll just say a sequence. Okay, so a sequence of random variables MP, and these are going to be real valued in a minute. Every time I say that I'm using expectation or L1 or something, it means that my random variables take values in the real numbers. I want to say something else. If I don't use expectation, then I can mean random variables taking values, some measurable functions into a general space, vectors, or maybe just a discrete group or something. Yeah. That will happen in the future. But when I want to talk about expectations, I have to have real valued objects. You don't know what to do when we take expectation of non-real valued objects. Okay? So these are real valued. You could do complex here, but it's real valued random variables empty is called a martingale. Okay, if one, they are all integrable. Two, you can always take expectations because again, I didn't deal with conditional expectations when I'm not in L1, right? Somehow I'm always using L1 in the background. At least L1. Some people we want to use L2. For martingales, we actually do want to use L1. Two is that for every t, I can look at the conditional expectation of mt plus 1. Okay, next step, conditional on. Now, remember, I'm allowed to condition on random variables. What does it mean to condition on random variables? I have a collection of random variables. I just take the sigma algebra generated by those random variables, right? So all pulling back with all the random variables, all possible Borel sets, and then, or all possible sets in the target sigma algebra if they're more generally valued, right? And taking a sigma algebra generated by those. So here I'm going to write the whole history. So I condition on the whole history, condition on all the games you played until now, and I'm asking for the expectation of your winnings in the next step. Where will you be in the next step in terms of winning, right? That's what this is doing. Think of the MT as the sequence. MT is the amount of money I have at time T after game T. Okay? So M0 is the amount of money I came in with, then M1 is after one game, M2 is after two games, right? So this is what it is. And what I wanted, well, for all T, something should happen, right? There's a condition here. So this should almost surely equal to MT. On average, you do not change. It's a very general, I mean, it's quite general, this condition. We'll see many examples. And in fact, in a lot of probability, the creativity goes into coming up with a martingale. When you find the martingale, it usually gives you a lot of information. Finding these guys is kind of the creativity part. After you have them, it turns out that there's a lot of theorems you can prove just under these conditions. It looks like there are not too many conditions, but actually it's very restrictive in a certain sense. So, in fact, we will weaken these conditions, maybe not today, but next week. Look at something slightly more general. So I'll already hint. I could also change this instead of for every t, this conditional expectation is equal. I could change it to be less than or equal or greater than equal. The averages go up, the averages go down. You can think of a game where you have an advantage, right? Or the casino has an advantage, right? So you could think of something like that.
Can you just condition on MT?
Or Markov chain.
Oh.
If I conditioned only on MT, then I mean, okay. If this holds, right? So who is the bigger sigma algebra? The bigger sigma algebra is the one where I have all of the random variables, right? So if I condition on MT, if I take all of this and condition on MT, right? Then it's the smaller one wins. It's the tower record, right? So the more general definition is defining it this way. Could be that it's different. Doesn't have it. Don't think of a Markov chain. Don't think of a Markov chain. Some Markov chains are can give you martingales. That's the deal with harmonic functions, but it's a special case. It's not the general case. We'll see. And in fact, I'll show you some examples today already. So now we could have done a more general. So more generally, so this is the definition, and I'm going to give an example in a minute. More generally, what we could have done was we could have defined what's called a filtration. Okay? So definition, I have a probability space. A filtration is a non-decreasing sequence of sigma algebras. They're all contained in F, but each one contains the previous guys. Okay? Example of a filtration is if I have a sequence of random variables, it's called index. Okay, any random variable, these don't have to be real value. And I define ft to be the sigma algebra generated by the first t guys, right? So when I make t bigger, I get more and more information. So the sigma algebras become bigger. Right? Pull back more and more events, so you get more and more things in your sigma algebra.
And then to exhaust the whole.
No, I didn't say that they exhaust. It's just a non-decreasing sequence of sigma algebras. The reason I want them to live in F is because F is my whole world. I don't know anything about anything outside F, right? It's just a technical. Okay. And what I could have done was I could have defined, so alternative definition is a martingale with respect to a filtration. Okay? The reason I'm talking about filtration is I will want to talk about, or sometimes it's easier to find out that a martingale is a martingale with respect to a different filtration rather than the natural filtration that comes with it. So here I'm using the natural filtration that comes with the sequence itself. Right? But so alternative definition of a martingale is that MT is a martingale with respect to the filtration. So you're given a filtration FT if one, I have to add a condition which automatically was satisfied there. So since I did 1 and 2 there, let me add it as a 3, okay? So 3 or 0 if you want, it doesn't really matter. MT is FT measurable. Okay, each MT, so this is for every T, of course, for every T, and then 2 and 3 are the same thing, okay? Except that you take conditional expectation with respect to the filtration, so T plus 1 with respect to T, you get MT, almost surely, of course, and this is for every T. And 1 is, again, that MT are all in L1. Okay? Okay, so this is with respect to filtration. Exercise. If MT is a martingale with respect to the filtration FT, then MT is a martingale with respect to the natural filtration
Part of the tower.
Natural filtration let's call it sigma of MT over T. Okay? So this definition is not weaker than the more general definition here. Here I made it more general because that definition is a special case of this definition where you take the natural filtration. It's not more general because every time you find the filtration for which it's a martingale, you know it automatically is with a natural. So that is that could be the definition. Okay, but you should know basically what this is saying, this exercise is saying, is that sometimes it might be easier to prove this conditional expectation than, if you put something else here, and because maybe this gives you information in a different way, and that's enough to give you the, okay? Okay, examples. Let's do some examples of martingales. By the way, exercise, but this is not really an exercise. If MT is a martingale, so from now on, I'm not going to say martingale with respect to filtration, because it's always with respect to, it's always also a martingale with respect to its canonical filtration, natural filtration. MT is a martingale. What is the expectation of MT? We know that MT is in L1. You can ask what its expectation is. What is it?
Expectation.
So prove that it's the expectation of M0. Okay. Whatever that happens to be. Okay. So this is true for everything. We'll see a much broader statement about this. I mean, we'll make this much stronger or useful, but this is already useful. So let's see some examples. I leave you with this exercise. It's not difficult. So, examples. Example 1, assume that t goes from 1 to infinity. These are IID plus minus 1/2. Okay? I have random variables taking values plus minus 1. If you want to think of it, think ut is what you win in game number t. And then I can define mt. Now mt is going to be a martingale, right? Because I use m. Don't have to, but it's going to be one, right? So I need something real valued. Oh, but I happen to already have these guys real valued. Okay? But you shouldn't think of these being real valued. These are taking values in a group, and I'm defining a real valued object. I'm going to define it by taking the sum. So I need to tell you what M0 is. It's going to be 0, okay? And I'm going to define the sum from 1 to t of u. Okay? So the empty sum is 0. Okay? Now, let's check if this is a martingale. So, in fact, I'm going to check it not with respect to the canonical filtration. It's not very difficult to do it with respect to the canonical filtration, but with respect to a different filtration. And we know that it's enough by the exercise, right? So that's, well, the fact that they're all in L1 and all measurable with respect to the filtration that I'm going to choose, this is easy. I'm not going to show it. But I mean, they're bounded, right? All of these guys sit between minus t and t. So they're not uniformly in L1 in a certain sense. We'll talk about what uniformly means in this context, right? Because they get bigger and bigger. But each specific one is in L1. Has absolute value, has finite expectation. In fact, they're bounded. Each one is bounded. They're not uniformly bound. Okay? So I'm going to condition on this filtration. Okay, now you can see that MT is, of course, measurable with respect to this filtration, right? Because MT is just the sum of these things. It's a measurable function of these random variables means that it lives in the proper signal algebra. But what is the conditional expectation of this guy? Well, we can write exactly what MT plus 1 is. MT plus 1 is equal to MT plus UT plus 1 right? This is an equality, by the definition equal. Now, conditional expectation is linear. So we take it apart. What is the conditional expectation of empty with respect to this sigma algebra? It's just empty, right? Because empty is measurable with respect to this guy. So this is, the first term becomes empty. And what is the conditional expectation of ut plus 1 with respect to a sigma algebra?
Independent.
The expectation of
It's independent of the sigma algebra. So
expectation of
it's the expectation of ut plus 1.
which is 0.
Right? When you're independent, you get the expectation, the actual expectation. Okay? And it happens to be 0. Miracle. We get empty, right? So, of course, all equalities are almost surely, right? There's no other sense. Okay? There, all the sentences I say, from now until the end of the course, each one happens almost surely, but since there will be only finitely many, so they all happen. Unless I make a mistake. Okay, so this is the first example, and if you think about it, this is a random walk on Z, right? Left, right, with probability half. But you say I could have changed this, could have done it differently.
You got lucky because of the miracle.
Right, but I could have changed. Right? I could have taken UT be independent, not even the same distribution, independent and expectation 0. And L1.
All you used.
Right? If I did that, instead of that, I would still have. Now, this is usually right. So in the second game, this is also true. But this is usually not called a random walk. Why? Because you see that I can change the distribution at different times of the step. You're taking steps. Okay, these can even live maybe on R, right? You're taking some steps in a uncountable group, which is weird. But you're taking steps on R, right? And so you have some process here. And but these steps could, ahead of time, that at time 100, you have to take steps sampled from this computer, and at time 500, you have to take from a different computer, and each one of them samples a different step distribution. This is what we don't usually call this a random walk. In terms of Markov chains, this is time dependent, it's not time independent. Okay, but this is still a martingale, so it's a much more general object than just random walks or things like that. Okay, much more general object than just. Okay. Okay, let's do another example. I'm going to start showing you why the U's don't necessarily live in R. They're not real valued. The M's will always be real valued, because if I want to say something is a martingale, I have to have real valued because I want to take expectations. So, example 3, let's take UT. Independent, okay, L1, but okay, let's make them so let's make them IID, just so that I don't have so these are going to be independent, and they're all going to have the same distribution. They're going to be, we could do RD, it's not so. They're going to be RD valued. Big values in RD, this is no longer R. I cannot take expectations of these. I mean, we could define, but don't have it. It's not in our language, right? It's too sophisticated for me. So probability that ut is equal to, say, some vector, okay? This is something in RD, okay? And the probability equal to that, it will be the same as the probability equal to that, will be, sorry, minus, here, this is what I want. I want it to be symmetric. Okay, so it's vector and it's minus get the same probabilities. And this is some number, which I will call mu of v, okay? And the support of mu, so mu is some probability distribution. Mu is some probability distribution v, okay? And the support of mu, say, is finite or something, because I wrote it this way, right? So this is some finite subset of maybe the unit ball. Just to make it bounded, so that when I take things, you know, they don't explode and I get L1. Okay. Now, okay, so we can look at this, then we can fix linear function. Well, what is a linear function in RD? It's just an inner product with a vector, right? So fix some other vector, too many u's and v, so let's use that. W, v, and define mt, so m0 is 0 as usual, and mt is going to be the sum 1 up to t of the inner product of my random u with w. Okay, which is the same as summing the vectors u and then taking their inner product w. So you see, I turned it into a real valued object. Okay, I claim that this is also a martingale. Let's do it in our heads. Well, first of all, these guys are in L1, right? This is just Cauchy-Schwarz or something, right? The norms of these things is just bounded because I made them all bounded. Not a problem. You know, this is just sums of things that have size at most some fixed number, which is 1 coming from this and the norm of W coming from this. So these are all in L1. MT is always measurable with respect to U1 up to UT because it's a function of them, right? And when you take the expectation of MT plus 1, what do you get? You get another independent guy, right? Added on. The MT comes out because it's measurable, exactly what we did with the random walks on Z. And the new one you take expectation of this thing. So the only thing left is to understand what is the expectation of this inner product. Okay? But that expectation is going to be 0. Why is it going to be 0? Maybe do it over here just so that it's to the same example, right? Why is it? So all I need to do is, okay, so the expectation of MT plus 1, conditioned on U1 up to UT, this is the same as MT because this part came out, plus the expectation, since U is independent, of UT plus 1 inner product W. This I'm allowed to take expectation. It's an L1 random variable.
The plus minus.
Yes. So an exercise to check that what is this? So I made it simple, right? I took some finite subset of the unit ball. We could have made it much more complicated and it still would work. All we need is that this thing has 0 expectation. That's all we need. But if you have a finite set and you distribute it symmetrically, then it has to be, because of the linearity of expectation, it has to be 0. So you want, we can compute this expectation. It's just you sum over all the guys in the support, right? And you take the probability that this is equal to that. It's a function of a random variable, a discrete random variable.
Just in terms of the definition, mu is a measure on RD, but like it has to, as you define the ut to give the same value for plus minus v's, and
Yeah,
they
so,
correlate in some sense, or
no, I'm just saying, what is the probability? You have a lot of vectors. Think of the support of mu as the standard basis and its inverses.
yeah, but if mu is given to 1, 0 and minus 1, 0 different probabilities, doesn't work with the.
Can't.
Right,
So
so
This is a condition. These two have to be equal
oh, you wrote.
to some number, to the same number.
what came first, the mu or the
So I said there is some probability measure to finite support who is a subset of the unit ball,
okay.
and it's also symmetric. That's what I defined. Okay. It's a special case. It could be much more.
No.
All I really needed was for this to be expectation zero. Now, why is this expectation zero? Well, it's because when I sum over all the guys into support and I have mu of v, then mu of v is the same as mu of minus v because of this condition, right? So I could write it this way. I could write it this way. Still gives me the same sum, right? Because when I split this into two sums, and it's finite, so there's no problems of convergence. And then when you see this is zero, right? So that's why symmetric measures gives you zero. Okay, not zero, but rather. Okay, so this shows that it's a martingale. Okay, it's upsetting. Okay. You see, it's a very general martingale. Now let me give you one more non-trivial one. Okay, one more non-trivial one. Okay, let's define a new sequence, same setting as before. So we have this distribution on RD. I mean, what you should, I made it too general for an example. I made it too general. What you should think about is mu is uniform on standard basis and inverses. You take the standard basis in RD, you take all the minuses of those vectors, right? So you have 2D vectors, and you just take uniform measure, each one with probability 1 over 2D. That's the simplest case. What is it? What is the sum of the mu's? What is the sum of the mu corresponding to? If you think of d equals 2, it's corresponding to going with probability 1/4 each one of the directions north, south, east, west in each step. And then the sum of the u's tells you where you are in the space. You stay on the lattice if you take the standard basis. Where you are in the space at time t, after t steps, right? It's a random position. And when you define the martingale, you just project that onto some direction, right? Let's define another one. Nt, I'm going to define it to be, so n0 is 0, and nt is going to be the norm of the sum. So my random position in RD, take the norm squared, okay? And I want to ask, is NT a martingale? Let's compute. Of course, measurability, L1, no problems, right? I mean, I kind of defined it in a way that it cannot escape. These are all bounded, and they're all measurable with respect to the the filtration of the U's, okay? But now, I want to check this.
Just some Pythagorean theorems.
Yeah. That's why I put a square there. If it was the norm, I would be in trouble. Okay, so I'm going to write out what this is. Okay, so expectation of nt plus 1 is this sum up to t plus 1. So it's this plus ut plus 1 squared. Okay? So I get nt, that's this squared, plus ut plus 1 norm squared, plus 2 times real part, but everything is real, so it's not a problem. Inner product between
What's inside?
yeah, so sum, I should have given this maybe a name. This is the random walk, okay, or corresponds to the random walk. And this inner product with all of this is conditioned on U1 up to UT. All of this is conditioned U1 up to UT. Okay, now let's see what we need to compute. This is measurable, pops out. Okay, so this is easy, right? Just itself. This is independent. It's just the expectation of this. Okay, so this is another easy thing. I do it like this to remember that it's a different one. Okay, and then I have to compute this. Okay, but the sum pops out, so I can do the sum, right? Okay, so we have to be careful about how we do those things. So this becomes NT plus the expectation of the norm of UT plus 1 squared. All of these have the same distribution, so that's just some number, right? That's just some number. You can compute it. So this we can call alpha. If you want, we can compute it, but it depends on mu, it depends on who you.
It doesn't depend on.
But it doesn't depend on t because of the way I defined these u's. Okay, so there's some number alpha. I mean, these are bounded, so I know it exists and everything is fine. And then I have the plus the conditional expectation. This is the more complicated maybe object. 2 times sum, yeah. So this is both linearity of the inner product and linearity of conditional expectation. Then I have expectation of UK conditioned on UK inner product UT plus 1, conditioned on U1 UT. Now I'm reminding you how we do conditional expectation, at least for the cases where we have discrete things in the conditioning. Right? We go over all the possible options for this. And for each option, we fix that option and we take the conditional expectation of what we have in here conditioned on that option happening. Right? So this is plus, okay, so we're only computing this guy. Okay. Now, usually what you'll see in my book is that I just do this in one step because I can already do it in my head, right? Because so I mean, but so I'm computing. Sorry, not the whole sum, but I'm going to compute this guy for specific k. It'll be the same for all the k's. But what's happening here? When I condition on a value of these, then I also have the value of UK. Right? Now, when I have the value of UK, then UK is a constant for me, a constant vector. Right? So I'm just taking the expectation of some symmetric distribution with some constant vector. Okay, independent symmetric distribution with some constant vector. So all I'm getting is something of the form of what I just erased, right? UT plus 1, inner product with some fixed W, right? Expectation. Okay, that's what I'm getting. So so it'll come out to be 0 because of the symmetry. Okay, but if you want, we can prove it, you know, very explicitly. Okay, so I'm doing just star for this computation, and what I'm going to get is this. So this expectation inside here is we have to sum over all the possible values for U1 up to UT. So let's do U1 UT.
You know that we only care about how you calculate the.
Right, so what are the possible, I have to sum these in the support of mu, right? Because these take values in support of mu. I have, you know, the support of mu t times.
You're referring to the formula we proved,
Yeah, the formula that we proved when you condition on a sigma algebra generated by a discrete partition, right? So you have a partition of the space into all the possible values, right? And then what we have to do is we have the indicator of the event that these guys are equal to these guys, right? So I can write it this way. For k between 1, for all k between 1 and t, u k is equal to little u k, right? Okay, that's the indicator that appeared in the formula yesterday. And then I have to take here the number, the coefficient in front of, so this is the random part. Coefficient now becomes the, again, the right way to think about it, just, okay, condition this guy is constant, I have inner product, this is symmetric independent of the thing, so it's 0, but, okay? But you have expectation, formally, I want to show you how you do it. You have expectation of, now what I want, I'm taking expectation of this inner product, is the random variable I'm measuring, right? Indicator of my event, all k between 1 and t, uk is equal to little uk. Okay, all of that inside the expectation divided by the probability. And of course, I'm only summing over the guys, well, I said in the support, where these probabilities are positive, right?
A lot of independent.
Yes. So now we're going to use independence. First of all, I'm looking at this indicator. When I multiply by this indicator, then this big UK is the same as writing little uk, right? Because otherwise it's 0 here, right? So I can just put a little uk here. Okay. And now I have a random variable and a random variable. This guy lives in the sigma algebra generated by this guy is measurable with respect to u1 up to ut. This guy is measurable with respect to, well, I mean, it is basically ut plus 1, right?
This is like a function of ut plus 1, so it's also independent of.
Yeah. So these are functions of u1 up to ut. This is a function of ut plus 1 because now I put the, I put a little arrow to remind us this is a little one, right? So now this is just some fixed thing, right? Which is a function of ut plus 1. So these two are independent random variables, right? So expectation just becomes the expectation of this times the expectation of this. Okay? Now, what I would tell you is that these cancel because the expectation of this is probability, so they cancel. I don't even need that because the expectation of this is 0. Right? We already said before that because of our symmetry, because the way we chose our symmetry, and if it wasn't symmetric, we would be able still to compute this coefficient here because of the independence.
This is basically a sum of zeros.
Okay, so it's a sum of zeros.
Mm.
So this whole thing becomes 0, and that's exactly what I told you before. The independence of this with this, and the fact that you know that when you have an independent symmetric distribution, the inner product will just average to 0. What you do when you do conditional expectation is you think of this as being constant, and you're averaging this conditioned on that constant on sigma algebra. But since it's independent, you're just averaging this inner product with something, and any inner product of this symmetric distribution is 0. If it wasn't a symmetric one, I'd have to take into account the different numbers, the different vectors that could come up in this thing and their weights. It would be more complicated computation. But anyway, this becomes 0, and so the whole computation using that gives me nt plus alpha. So is it the martingale? Depends on alpha. Alpha is not going to be 0. No negative thing.
And don't we know that it's supposed to be 1 by our mu?
I don't think it's supposed to be 1. It doesn't have to. Well, standard basis.
Yeah.
Yeah, maybe. 1, or do you get? Well, it's some number. But now I'm not even talking about standard bound. Although my only assumption on the distribution is that it's bounded and it's symmetric. Okay, I get some number alpha, and this is not a martingale. So nt is not martingale. Okay, but what if I define nt? Nt minus alpha times t. And of course, m0 is 0. Okay. Then when I take expectation, mt plus 1, conditioned on u1, ut, right? Again, of course, they're measurable. I just added a constant. I didn't do anything about measurability, right? Then what do I get? I get, because the alpha is independent of t, this is very important. If the alpha depended on t, I would have to sum the different alphas here. Each one for a different t. That would still give me something, okay? This is a very useful trick. Kind of what you want to do is you have something, you want to understand this object. You want to study this object. You can understand how it evolves when you take conditional expectation with respect to some natural filtration that you have. But you see, it doesn't evolve like a martingale. There are some error terms. Well, you kind of reconstruct your martingale to take care of those error terms, right? And so when I do this conditional expectation, then I get nt plus 1 conditional expectation that said nt plus alpha, right? The nt plus 1 part here gives nt plus alpha. Then we have minus alpha times, remember this was t plus 1. This was just a constant. Just a constant. There's no expectation, no, it just comes out, right? You see that the alphas cancel, and if it was different alphas, it would be a sum of alphas, and the last one would cancel, and that would still be fine, right? The alphas cancel, so I get nt minus alpha t, which is nt. So mt is a martingale. Or you have a very nice conclusion. You take this kind of, you didn't say what a random walk is, but you take this kind of random walk on RD, right? With a symmetric and bounded distribution. The steps are bounded in size, right? They're in the unit ball, but we could have taken any bound. And they're symmetric. It was important they're symmetric. Everything here hinged on the fact that they're symmetric. Then this thing will give you a martingale. And alpha will be some number that you can compute coming from the distribution of the steps. Okay? And not only that, I can tell you what the expectation of the norm of your position at time t, or the norm squared. Right?
It's alpha.
This is expectation of nt, but I mean, that's what it is, right? And nt is not a martingale, but I can write it this way, expectation of nt plus alpha times t. Alpha times t is a constant. And even if they were different alphas, it would be a sum of alphas, right? Okay. But the expectation of mt is expectation of m0, which is constant 0. So this is alpha times t. You can compute alpha. Alpha is a function of mu and what we defined.
Okay. Is there any interpretation of this alpha, what it means?
Yeah, alpha is the speed. Alpha is not the speed, but the diffusivity constant. Okay, I'll tell now I have to tell you a story about it. I didn't realize that we need to take a break. Okay, so you should have told me. Okay, so I'll tell you a story, then we'll take a break. Okay. In the 19th century, you know, a guy named Brown was looking at the milk or something, and he saw in a microscope, and he saw the particles were kind of moving around, and he said this function, the movement of these particles, so they're moving in R2, for example, right, or part of it. He said this reminds me of the functions that mathematicians say exists, but of course do not exist, which are continuous but not differentiable. So the movement of the particles was they were like, you know, jostling around. So they're continuous, of course. The particle does not appear somewhere. It's not quantum mechanics, right? But it kind of like changes direction very non-differentiable, in a non-differentiable way. Okay, the derivative is it doesn't exist. So when Einstein eventually in 1905 wrote three breakthrough papers, right? One was special relativity, which he didn't get anything for, just international fame. Another one, which is the photoelectric effect, which he also proved basically the existence of atoms and solved the long-standing problem, right? No, sorry, another one was a photoelectric effect, which he explained the black body radiation and stuff like that, and he got his and he got the Nobel Prize. That, not for special relativity. And the third one was his PhD. And this third one was about Brownian motion. Now, Brownian motion is exactly the motion of these particles, and Einstein gave a model. Basically, it was a model that the big particles have little guys bumping into them. You can think of molecules, because the big guys are much bigger than molecules, right? You need a microscope to see them, but they're like little seeds or pieces or things. The molecules are much, much smaller, or the atoms, they were talking about atoms, are much, much smaller, and the atoms are bumping into them. So Einstein's model was that you kind of, at each moment, you add to your velocity. Now, velocity is a vector, right? So you add a random vector in a maybe uniform direction with some fixed size. So choose maybe uniformly so it's a sum of, where's my sum? It's a sum of random vectors in space, right? In the plane or something like that, where they are chosen from some symmetric distribution. Now, you can do this whole exercise if we change mu. We used finite support, right? But if we took like uniform on a sphere, everything would still work. You'd have to maybe you have to compute why the expectation there is 0, but it would still be 0. Okay, you need to do integrals, but
It wouldn't be discrete.
yeah, it wouldn't be discrete. So you'd have to understand something about conditional expectations. Use a density theorem or something like that. It would still work. And what Einstein did was he computed things. For example, he showed that this constant was important for things to diffuse. But what you should see is that what's scaling linearly with time is not the distance to the origin, to the starting point, to 0. I mean, we set 0 to be our starting point, right? So it's not the distance, but it's the square of the distance. So actually, on average, you're escaping at a rate of square root t. This is called diffusive behavior, because this is what they see in all of these, natural models, the diffusing things. They're diffusing it. And in fact, this is what happens with heat. And Einstein tied this to the heat equation. And he said, particles are moving like heat, and he made many connections. And in fact, this is considered the proof that atoms exist. They didn't have a direct proof that they're atoms. But the fact that the model was exactly, the calculations and the theory were giving exactly the right diffusive behavior. So I don't know all the details, but that's the story about this constant. And the interpretability of this constant is basically temperature. Because you raise the temperature, atoms are bumping into you. So you're taking these, they're still uniform, but they're maybe have bigger length, or maybe they have a distribution on lengths. And the higher the temperature, right, you get larger and larger momentum. You get larger, conservation of momentum tells you that your jumps are going to have larger distribution. Maybe not on a sphere, maybe it's in bounded between two spheres or something, but it's going to be symmetric, and it's going to kind of have, bigger and bigger. With higher and higher temperature, you will have bigger and bigger alpha. Remember what alpha is just one jump, second moment of one jump. Okay? Alpha is temperature, and it's very deep. I mean, it's not trivial at all. But for these simple objects, we can already study them. I mean, Einstein didn't have this language, of course, and he was also doing it in continuous time and space. It's more difficult in this case. Just for technical reasons, not really. I mean, if you want to study Brownian motion, it's better to study random walks. It's just easier to define, and you get all the phenomena. Except for the fact that non-differentiable functions. Okay, so let's take a break and so we come back at 11:30. Since we started discussing this, let me just say one more thing about this. I wasn't planning on saying, but I want to show you something about this diffusivity constant. When you have such a situation, right? Remember, So think of the one-dimensional situation. So now I just have so ut are independent, real valued. Each one has mean 0, and maybe they all have variance 1. Okay. Okay. I didn't say they have the same distribution, right? So we can look at their sum. Right? So this is the kind of the random position. We know this is a martingale, right? But we also know from what we just discussed is that if I take this in absolute value is the norm, right? And squared, and I take the expectation, right? Then this is equal to, what is it equal to? It's equal to alpha times t, where alpha, sorry, it's not equal to alpha times t. But rather, if you do the computation, right? We said when we have different alphas, right, then we have to sum them for it to be a martingale, right? So when you sum these guys, right? So you're summing actually the expectations of the individual ones, right? So this is the sum, the expectation of the individual. Now, of course, this is true. This is just Pythagoras theorem. This is the variance of the sum is the sum of the variances, right? That's what it says here. They're independent. Okay?
Independent, it's like orthogonal in a sense.
No, yeah.
The-
Why do I call it Pythagoras? I just this is basic theory in probabilities that this is a mean 0 object. So the square expectation of the square is the variance. Okay, and the variance of the sum of independent random variables is the sum of the variances. That's all I'm saying. That's what I call the Pythagoras theorem. Yes, independence is like orthogonality, but in some much broader space. So you see that this kind of has to do with these things, and also you see that if they all had all have yeah, so sorry, so this was the sum if I had all the alphas, but if they all have variance 1, then this just becomes t, or my alpha is just 1, right? And you can also, alpha is just the variance, so you could, right? So you see that this thing is scaled like t. So if you expect anything to happen in the limit, then you already see that you have to scale by square root t in order to get some meaningful limit. Okay, so right, if I want this to converge, I want the variance to stay constant, then I need to scale by these things. So you see why the square root t scaling is what you expect. Okay, just from the central limit theorem. But this is kind of much more general than the central limit theorem. First of all, these could live in a high-dimensional space. In fact, in a Hilbert space, they can live and make it much more complicated. And then you have to be careful, conditions, boundedness, and things in L1 and things like that. But you can do computations. So, and we'll see how to do better computations using this martingale and the original sum as a martingale. We'll be able to do some computations very easily. Okay. So now I want to go into a detour in order to prove the martingale convergence theorem. Okay, 2 theorems I'm going to prove about martingales. Okay, 2 important theorems. Of course, there are many theorems about martingales. The martingales has a very rigid structure. So the 2 theorems that I want to prove. Of course, I won't prove them both today, but 2 theorems. One is martingale convergence. It basically tells you, there are always some conditions, but basically tells you if you have a martingale, then it almost surely converges. So you have a sequence of random variables and they converge to a limit. The limit is a random variable as well, but the limit exists. So almost surely the limit exists, not lim sup, lim inf, right? But almost surely those 2 things are equal. Okay. That's one thing, and this is very, very strong. This is a very, very strong thing. For example, I will be able to tell you many things about harmonic functions just using this fact. Many theorems, you can give a one-line proof using martingale convergence, and sometimes you can give even
That you don't have non-constant harmonic functions that are positive on Z2.
yeah. So, for example, yeah, we'll talk about this. And two is what's called the optional stopping theorem. Now, the name optional, not because it's optional, but rather it's because it comes from the world of stocks and options. Okay, why does it come from stocks and options? I have no idea. But if you write optional stopping theorem, you'll just get papers, and you'll get millions of papers in economics. This is what they do all the time. They talk about. But what you should focus on the words here. I'm going to always call this the OST, and just because this is what it's called. I think historically they kind of developed this theory for the martingales were used historically to study options and things like that. Black Scholes, they get the Nobel Prize, Ito calculus, things like this from economics. But the optional stopping, you should think of these words, not remove the option. So it's a stopping theorem. Stopping theorem will tell me that if I stop at a certain point, I can still measure the expectation and know what it is. So we've already seen kind of a stopping theorem. We've seen that if you have a martingale and you stop, right, then you know the expectation. It's just, right, for martingales, you know the expectation at time t. It's the same as at time 0. All the expectations are the same, right? So, but the optional stopping theorem will tell you something. This guy can be random. You stop at a random time. For example, you can stop at the first time the random walk does this and that. Okay. Now there are some conditions, so we have to be careful, and we have to see what the conditions are. And in fact, there's a whole area of research of such theorems. Will prove something fairly general, but not the best thing you can do there. Better and better, more and more general things you can prove. But these are the two things I want to use, and they give us a lot of flexibility when doing random walks. Okay. These are the things that from the theory of martingales that I'm going to want to use. So we're going to start with the martingale convergence. In the book, it's in the opposite order, and I kind of regret doing it in that order. But there are advantages to doing it this way or that way. Logically, martingale convergence should come first, but pedagogically, this one should come first. That's why I did it in the book. And then there's you use this here, and then you have to say that in the future we'll prove this. So let's move to martingale convergence. Okay, and we start today and hopefully finish it. So first of all, I have to generalize the definition of a martingale, what's called a super martingale or a sub-martingale. Okay, and this is what I told you that we do. Never remember which one is which, but that we do inequality signs instead of equality signs in the sequence MT, real valued random variables MT, being very careful, is a sub-martingale. I think I'm only going to use sub-martingale. Maybe we should yeah, let's just do sub-martingale. You can imagine what a super martingale is, okay? So sub always refers to the process itself with respect to the conditional expectations. Okay, so I never remember this, but it's a sub-martingale if MT is 1 for all T measurable with canonical filtration. We could also do it with the general filtration. I'm not finding everything, and so if mt is in a 1 for all t, and the expectation of mt plus 1 conditioned on m1 up to mt or m0 up to mt is, so sub means that this one is small. Right, so this is sub-martingale. I always confuse them. Okay, and another thing I want is that a sequence ht is predictable with respect to mt, respect to the process mt, if ht is measurable with respect to t minus 1. Okay, that's what I want. That's what predictable means. Like I can. Okay, so if ht, I can write it this way: is in means measurable with respect to, you do from m0 up to mt minus 1 for every t. Okay. Just a word, it's not so important to remember this. But let's give some examples of submartingales and or maybe I give it to you as an exercise. Okay, so one nice way of submartingales. So examples. I'm just showing you how it's easy to work with these things. Why we want this sub? It is just easier to work with them and not worry about equalities. I could have done everything with martingales and had to be careful about defining things. But then it just makes it quicker if we just put in these
A
definitions.
minus mt, right?
Right. So first of all, any martingale is of course a submartingale, and also a super martingale, right? Because equality is inequality. But we could also do if mt is a martingale, then we can look at the absolute value of mt. Now, what do we need? Now, what happens when you put an absolute value on these things? So the expectation of the absolute value, right, is bigger than the absolute value of the expectation, and then the absolute value becomes mt, right? So it works in the correct direction. Otherwise, I put a minus. But so then mt, this process is a submartingale. Okay.
It's sort of like harmonic and subharmonic.
Exactly. It's the same thing. Exactly the same thing. But in the world of harmonic functions, there's a very big difference between harmonic is much more restrictive than sub or superharmonic. And what other example? Oh, okay. So exercise. Exercise. Suppose that I have already a submartingale. And I have some real number A. Okay, suppose I started with a submartingale. This is not a martingale anymore, submartingale. And I define a new process, mt minus A, times the indicator that mt is bigger than A. Greater or equal? What do I want? I think it doesn't matter, but I wrote bigger in my notes. I think it's also true if you do it. Right. So this is a new sequence. Now, even if this was a martingale, this is not going to be a martingale. I mean, this expectation, for example, is always greater than 0, right? Or greater or equal than 0 at least, right? Probably not 0, right? This is a non-negative random variable. But what happens is that if you start with a submartingale, then xt is also a submartingale. So you see, I can do more general things with submartingales, things that I can't do with martingales. Okay? And So I'm leaving you to solve this exercise. It's not very difficult. I mean, conditional expectation. You just have to satisfy some inequality. The L1s and the things are easy for fixed numbers. And the other one I want is slightly more. So this exercise, if we can do it together, finish with this. Oh yeah, so let's do this exercise together. Okay, so the exercise is like this. We have a sub-martingale given this, and we have HT is predictive. Okay, this is what we are predictable with respect to MT, right? Which is this definition. And then we look at the following process. We define a process. The notation is H dot M. Okay, what is H dot M? This is kind of, this notation is from Doret, but it was kind of accepted in also in older texts. I don't know if it's so great. So I'm just defining a new sequence. H dot M at T is you sum from 1 to T, and you use this difference, okay? But then you multiply it by this H. Okay? So we have all of this information, and now we're going to put in an assumption. Well, we already had an assumption of a sub-martingale. Assume that HT is non-negative for every T and bounded. Huh?
I think we saw it in the Yair course about we want to say that the expectation is 0 or something like that, that you can, he said it like a game of gambling when you know what you made so far, and H is like the next move. We want to say that you can't, the expectation is 0. Isn't it? Is it correlate with something I said?
I don't see how.
Did something else.
Or no, maybe I'm just like messing.
What I'm thinking about here, and what we do in general in this case is, if I sum this and I just get empty, right? The telescopic sum. This H, you can think about as telling me when to stop. Okay? HS is going to tell me at time S. Now H has to be predictable, so H has to be measurable with respect to MS minus 1. So I have to know if in the next step I'm stopping or not. Okay? So H could be like an indicator, you stop at the next step or not, or you don't stop, right? So it'll sum up to some random time. Some time which is, the more you advance, the more knowledge it has of, it can take into account the whole history of when to stop, but it cannot take into account the future. So that's what I want to think about. But it's just a kind of general formulation. It's not too intuitive, really. So so we assume that H is non-negative and bounded, okay? And predictable, right? Then what do we want to prove? Then we want to prove then prove that H dot M is a sub-martingale as well, okay? Okay. Also, if H so when I say bounded, I should say They're all bounded, I think. We'll see in a second what we need. But in my application for this, I'm thinking of all the HTs are between 0 and 1. So if HT is only bounded, not necessarily negative. Okay, so if your bounds are just from below and above, but not necessarily 0 from below, but MT is a martingale, so I strengthen the condition on M and weaken the condition on H, then H dot M is a martingale. Okay, so these are the two things that I'm going to want. Okay. So, any suggestions?
Linearity.
Well, I mean, we want to prove that something is, measurability and all that, these are kind of for free. We want to prove that something is a submartingale, so we need to take the expectation of, right? So we need to do the expectation. We do it this way, H dot M at T plus 1 minus H dot M at T with respect to filtration. Let's do the M filtration, right?
Why are you doing the difference?
Well, this is measurable with respect to this thing.
Right.
Okay? And so the conditional application of this is just itself, right? So all I need to show is that this object is non-negative for submartingale and equal to 0 for martingale. It's the same thing, right? It's because I have sums, so it's easier to look at these kind of differences.
You know what it did.
Right? I mean, if I would have started with this, I would write it as this plus something. And this will just pop out. Okay? So this is equal to, what is it equal to? Well, the leftover term is the T plus 1 term, right? So it's H T plus 1 times M T plus 1 minus MT. All of this conditional expectation with respect to 0 up to. Right. Okay. Now, HT plus 1, HT is predictable, non-negative. Okay? And predictable means that it's measurable with respect to this.
So HT plus 1 MT pops up.
So HT plus 1 pops out, right? So we get that this is, well, this is measurable with respect, but this is not. So the difference is not necessarily measurable with
Yes,
respect.
I'm saying you can pop it out with MT. Or you just want to.
Which one? This empty.
Yes.
Yeah. The second one will be HT plus 1 time, but then I have the first one inside. Like,
Oh, so when you
I
have
will be left with this, but you'll see it's the same thing. It's the same. Okay. So I have HT plus 1 times the conditional expectation, so almost Shor equality, of course. Times conditional expectation of MT plus 1 minus MT relative to conditioned on the. Now, again, I could have taken this outside, it would be what you said, right? So, but this difference again, now, so this splits into two things, right? Splits into two things. If this is non-negative and this is a submartingale, then this is non-negative. And so we get non-negative times non-negative is non-negative, right? So this is greater or equal than 0. If HT plus 1 is greater or equal than 0. And actually, I didn't need bounded, right? I didn't need bound. Oh, I needed bounded for it to be L1. I needed, so I need somehow to say that H times M is L1. That's somehow. So if I put in bounded guys here, then they don't change the fact that this is L1. That's why, right? So this is greater or equal than 0, so that HT plus 1 is greater or equal than 0. When HT was 1 and MT is a submartingale, right? In this case, then I have non-negative times non-negative. I get something non-negative, so I prove that this is a submartingale as well. Okay. In the other case, where I don't know anything about HT plus 1, but I know that H is a martingale, you see, I get that this is 0, so I don't care what HT plus 1 is. Right? So, yeah. So, right. So I want you to notice that bounded was for this to be an L1, and then I need a uniform bound on the H's, or at least some, it's not a, it's a sufficient condition for H. So the H's are uniformly bounded. Okay? Right, because I just bound this by then, and then the differences are all bounded by
It's
zero.
required H times M is in L1 for every T, right?
Yeah, yeah. You need some condition to guarantee that the new process H dot M is in. Okay, so when MT is a martingale, right, I don't care about anything about H, I just get equal to 0 here. And so that's a martingale as well. This is the exercise. Usually in these things, it's very easy. You just have to try to compute things and pull out the things that you know you can pull out. So, by the way, if we start again, if we started with this, then we would have that, and then we would just have this, we would pull this out, and the conditional expectation of this would either be greater or equal than MT or equal to MT, depending on the case. Yeah, it'll be the same proof. I just wrote it slightly different. Okay, so let me just say, so next time we're going to use all of this to, well, first I have to introduce stopping times because this is, we need this to talk about.
We need to bring money to buy some options in.
Yeah. We'll talk about stopping times, then we'll do martingale convergence. Martingale convergence has a very, very beautiful trick to it. You want to prove that some random sequence converges. What you do is you fix an interval of numbers, okay? Right, you have a real valued sequence, and you count how many times your sequence was below A and then crossed to above B. That's 1. Then you wait until it comes below A again, and you start and goes above B, not in one jump, but in right, and that's 2, right? Then you count 2, and you keep counting every time you see it below A. You wait. If it goes again above B, you add another, and you count how many of those. And what you do is you bound. So you show that the probability that you do this infinitely many times for any pair AB is just 0. Okay, and that means that for any rational A less than B, probability that you'll do infinitely many of these things is 0. So the probability there exists a rational pair like that is 0. But you can show that if your lim sup is bigger, strictly bigger than your lim inf, there has to be a rational pair such that you've done this infinitely many times. Right? So this is a super ingenious trick. In fact, I was hoping Alanka would be here today because it has to do with some something she proved, and I think that this would make her proof similar. But when looking at the proof of the martingale convergence, I was reminded of this a beautiful trick of. So it's a nice trick. It's called the up-crossing lemma. So where you cross, bounded intervals, and basically you can use that to show convergence of sequences of random variables. Okay, so this is what we'll do next time. Stopping times, up-crossing lemma.
תודה רבה.
תודה רבה.